It's my pleasure at this point in time to introduce my colleague, friend, and co-director, Professor Katsarkov, who will introduce the first speaker of the evening.
Thank you, Steve. So once again, thank you all for coming. And so our first speaker today is Professor Mina Teicher. So Mina is educated by the first wave of top Russian algebraic geometers who moved to Israel, like Boris Moishezon and Ilya Petetsky-Shapiro. So they very quickly moved to the United States, but she seized the moment and got her education in Israel while they were there. So eventually they became professors in Columbia and Yale University. Her early work included the solution of well-known conjecture on algebraic surfaces, so-called watershed conjecture, where together with Moishezon, they developed a technique of Braid factorizations, which today is quite used in symplectic geometry. So Mina later moved to more applied topics, and you'll hear more about these topics today. But let me just say that this is one of the many different kinds of works she does, not only in mathematics, but in all kinds of general society involvements. So probably I have never seen a mathematician that works with politicians on such a level. So actually I overheard conversation between her and Ariel Sharon in the old days. Luckily I don't speak any Hebrew. So Mina was a part of the Israeli government at that time. And then she communicates with people like Michael Bloomberg, George Bush Jr., and Bill Clinton. I've seen the pictures, so thanks for that. So in fact, she serves on many committees in Europe connected with ERC and all kinds of European foundations. And so she can be seen also as a certain type of 21st century Gertruda Bell, who is probably well known for her connections with Arabic countries in the 19th century. In fact, in my humble opinion, if Mina was involved in the solution of the Middle East crisis, there will be no more Middle East crisis. So let me let on you Mina Teicher, who is going to tell us about math in nature.
Thank you very much for this, I cannot say kind introduction. It's more than that. I'm sorry my mother is dead too. But, thank you for inviting me and giving me the chance to speak here. It's really a great honor. I don't have much time, so I will talk generally, even though I wanted to reflect to some of your remarks. Math and Nature is the title of the talk, but the message that I want to give is that mathematics is everywhere, really everywhere. And when I say everywhere, it's in God-made and in man-made entities. So when we talk about nature, you need mathematics if you want to study shapes and structures of different entities, live and still. If you want to try to understand processes, to understand the physical world, global warming, how does the brain work, cognitive processes. And when we come to biomedicine, which is one of the titles of this series of talk, you need mathematics if you want to identify and cure medical conditions, like those that are listed here. But mathematics is also everywhere in man-made. You need mathematics to study architecture and art, to design buildings and products, and to go into space, or to develop artificial vision and smart cities, a health system, financial market, mass transportation, and of course the computer of the future. We heard a lot about quantum computer and cybersecurity, which is the main goal now of many, many countries and many private companies. This is the threat to humanity. So without mathematics, you cannot face cybersecurity. But you cannot talk about everything in 45 minutes, so I will concentrate on nature And even then, I cannot talk about everything which is there. So I chose a list of topics from this nature. You see the list of topics here. I will not read it, but you come to it every moment. I just want to say that this is, that I might disappoint my mathematical friends because this is a public lecture, but so I'm not talking about how, I'm just talking about what. But any mathematician that want to understand the how later, I'll be more than happy to explain. So this is, and the last general remark that I'm very glad that the Hemisphere Institute is taking upon itself these public talks, because reaching the audience is not only service to the audience, it's also service to mathematics, because these people from the public are sometimes those that give money, and sometimes they are the clients of what we are doing. And very nice that the two first speakers are female. This is also, I appreciate very much. I think it's part of the Hemisphere Institute mission. Okay, so I start with the first series of examples of mathematics describes nature. So the first one that I take is the golden section, which is very familiar notion for a lot of people. And this is actually just a number. Even though you heard a lot, you saw movies, this and that, it's a number, 1.16.
No, just 1.6.
Made a mistake in the number?
Yeah, the small second one, yeah. 1.6.
Ah, okay, sure. Okay, it will appear again because I copied. So this number, why is such a number? It's not even a rational number, and there are all these dots there that sometimes it's not easy to understand what are they coming from. So where does this number come from? It comes from a rectangle. You take a rectangle that the longer side and the shorter side have a certain property. The property is that the longer divided by the shorter one is the sum of both of them, b plus c, divided by b. And the claim is, no, it wasn't copied. And the claim is that b over c equal b plus c over b. If this certain relation between the size of the edges satisfy that, then b over c, the number is 1.618. And this is very easy. The proof is very easy. This may be the last mathematical you see. It's something from junior high. If b over c equals b plus c over b, then we open the brackets and we call b over c x, and then we multiply everything by x, so we get a quadratic equation. And if we solve this quadratic equation by the well-known formula, we get that x is 1 plus square root of 5 over 2, which is 1.618, and 0, and that's where the dots are coming from, because the square root of 5 is not a rational number, so there are many dots there. X is often denoted phi and called the golden section. Leonardo da Vinci, the great Leonardo da Vinci, he observed that the golden section is observed in a well-proportioned human bodies. And in the Congress of Mathematics Education in Seoul in 2012, they had this kind of device that you can move it a little bit, and the people can put the center, move it, that it will be in the navel, and then the upper part versus the lower part satisfy the golden ratio, the golden section. It took me a lot of time to move all the other girls. They were very long lines in order to be able to take a picture that you can see the device. Everything is to raise awareness to the existence of mathematics in your everyday life. But it's not only bodies, it's also in faces. In the past, it was believed that beauty depends on very precise ratio between vertical and horizontal. Vertical between A and B, in the edge of the mouth and the pupil, and the length of the face should be 0.36, and horizontal between the two pupils and the width of the face should be 0.46. Is this the secret of beauty? Girls are asking themselves. Turns out that women known to be beautiful fail to satisfy this criteria. On the other hand, in all culture, for men and women, beauty is based on how closely one features reflect phi in their proportion. And it is hardwired into our being without even explaining to ourselves why we think that. And it's not a particular phi of certain ratio. It's certainly phi in the face. So it's already from antiquity. The goddess Athena has very precise golden section, vertical and horizontal. But also in very modern faces, and you see men and women and different races, but there is no one specific shape or distance that should satisfy the golden section. It's as many golden sections in the face that exist, regardless of what. And it doesn't have to be that one or that one. Once you have as many golden sections, then generally that's what you are considered. And it's also in a very refined places, not in the general face, a very refined one. And it's also in animals. The dolphin, we consider the old dolphin very beautiful. It has a lot of golden section in it. And the tiger is also considered beautiful, and it has it there. And not to talk about the butterfly that sometimes is a symbol of beauty. And there's many, many, many golden section there wherever you put this kind of scissor. They're helping to determine the golden section. So this was for the appearance of the golden section, and that's, you might understand why the Renaissance artists called it the divine proportion, because it appears so often. So you hear a lot that beauty varies by race, culture, and era, and you many times say beauty is in the eye of the beholder. But from now on, you don't say it anymore. You say beauty is in the phi of the beholder. And I'm writing a book now with a journalist from the New York Times. I'm talking, she's writing, and the name of the book is Mathematics of Beauty, and this is the slogan of the book. And she said, I should never mention it before the book is out. But I really like Miami, so. Okay, the next one is Fibonacci numbers. Where do we see Fibonacci numbers in nature? Fibonacci numbers is a series of numbers. Each of the numbers in the series is just a number. But together they make the series, and the property is that every number is the sum of the previous two ones. So 0 and 1 are random and maybe natural choice, and then 1 is 0 plus 1, 2 is 1 plus 1, 3 is 2 plus 1, 5, 3 plus 2, etc. A Fibonacci rectangle is a rectangle that the edges are two consecutive Fibonacci numbers. So 55 and 34 are the last two that you see on the slide. The previous one is 34 and 21. Now, if you turn it 90 degrees, and then you can move it and put it in the big one, because the smaller edge of the bigger one is the bigger edge of the smaller one, so it fits inside. And what is left a square. So a Fibonacci rectangle is a square plus a smaller Fibonacci rectangle. Now you take this rectangle, square, and a rectangle, and you put in the square that is left, you put a fourth of a circle. And then you do the same on the other Fibonacci rectangle, which is a smaller one, and you take out from here a square, and you get a smaller rectangle. And you keep doing it. Take a square and get a smaller rectangle, and every time you do a fourth of a circle. It's never the same radius. The radius is getting small, so it's not the same. But at the end, you get some kind of a spiral. And turns out that these spirals appears in shells, in different shells, appears in plants, in a cactus, in a rose, and in a sunflower the very famous sunflower. You see it's not circles, inside it's the spiral. The third one, the third appearance, comes from two-dimensional mathematical tiling. I leave the tiling for a moment and I talk about crystals in nature. So solid structure in nature, minerals and stones are called crystals. And they are three-dimensional, that's the idea of this crystal. And they are atomically built, not what we see from the outside, from inside. They are atomically built with symmetry and periodicity. And the symmetry can be twofold if it's 180 degrees rotation, or threefold, or fourfold, sixfold. And it was believed that all solid structures in nature are atomically built with symmetry and periodicity. No solid structure with symmetry and no periodicity. But in 1982, Dan Sheftman from the Technion in Israel, he predicted that there exist nature-made aperiodic crystals. He was then assistant professor in an American university, and everybody in the world was laughing at him for predicting that, and in the end he lost tenure. So he came back to Israel, started from the beginning, but in 2009, aperiodic stones were found on a Russian mountain. The story goes with a small stone shop in Pisa, that something was found, but anyhow it was found on a Russian mountain. So immediately, 2 years later, he got the Nobel Prize. You cannot get a Nobel Prize if you don't have an experiment to show your theory. So that's why theoretician cannot get the Nobel Prize.
Actually, Shechtman did produce a quasi-crystal around 1984 from an alloy of manganese.
But then he explained to me that that wasn't natural, that was made in the lab.
Yeah, it was made in the lab.
Yeah, but they talked about the nature made.
Yeah.
I should have mentioned that. The new structures are called quasi-crystals. So where is the math coming in the picture? Well, tiling, it comes from tiling. Tiling is covering a two-dimensional plane with no gaps and no overlaps. Wallpaper tiling respects symmetry and periodicity. For example, in this picture, if you turn it 180 degrees or 90 degrees, you get the same picture, and also it repeats itself. That's why it's called wallpaper. Wallpaper has to repeat itself because the guy is cutting it in different places, and then it has to be the same in on the whole wall. And these tiling are known for centuries, but there was no example of a wallpaper with symmetry and no periodicity. Till in the 70s, Penrose constructed a tiling with symmetry and no periodicity that has this 5 structure in the picture, and these were called Penrose tiling. And short after that, Shechtman predicted the existence of the quasi-crystals. And I asked him if it was if he was influenced by that, and he said that it wasn't that he was influenced, but he heard that there is something in 2 dimensions. He thought it would be 3 dimensions, but he had other ideas in chemistry to produce it. But for me, if he heard that there exists 2, then he thinks there is 3. This is what mathematics is about. You take 2 dimensions, you have some property in 2 dimensions, you test it in 3 dimensions and 4 dimensions. You come to 5, there's always some counterexample, but this is what mathematicians are doing, and he did it. So a quasi-crystal should have in its pattern some polygon with 5 edges. And this is actually the 3-dimensional version of Penrose tiling. I don't talk about, but you cannot do mathematics of entities without showing snowflakes, even though we are in Florida. The last piece here is the mathematics of hair braids. Okay, Lida, this is Lida by Leonardo. Leonardo comes again to the picture. He was really impressed by braids. And this is Lida, and there are many, many other drawings. Hair braids usually woven with 3 strands. This is the classical braid. But in mathematics, we also have 2-strand braids, 4-strand, 5, and n-strand braids. So in the modern, this is a strand braid. We think about the braid group of order 3, 4-strand or braid group, and mixed strain braids like this one, is of course can come of the inclusion of the different braid group. Leonardo was also very fascinated by the dynamic characterization of braid, and he has a series of drawing how braids transformed into water. And the mathematician asking about this dynamic, how braids relate to each other, formed, ordered, factorized, and the structure of the group of all braids. I studied it, as maybe mentioned here, and together with my student, we proved that one braid cannot be always deformed to another braid by conjugation. This is a very general, vague statement of the mathematics behind it. But then people say, okay, so how is it related to life? What does the result mean, the Lieberman result means for hair braids? I don't know. I decided it means that one needs to wash his hair in order to make a new braid. So that's it. So now we're coming to neuromedicine. That is under our title. So neuromedicine, first we have to know what do we know on the brain. So we know a lot on the brain. We know anatomy of the brain. We know that the brain has, we know the different pieces of the brain. We gave names to the different pieces of the brain. Some of them exist, some of them we made the name. Then it's more a picture from the side, a picture from inside. And we know that there are 10 to the 10 neurons in the human brain. It's a lot of neurons in human brain. So it's a very mixed forest. That's why it's not easy to understand how it works. We know there is white stuff between the neurons that give food to the brain. And we know that a neuron is made from a, something went wrong, that the neuron is made from the axon and dendrites. So this is just one cell. And the dendrites could be very long. It's approximately the shape of a tree. Sometimes if it's a mathematical tree, it might not be a mathematical tree, but the shape of a tree. Dendrites are traveling very far. The motoric dendrites go down very far to the leg. So if it's a giraffe, it's very far. We know that the brain acts by synapse. That's the way that electricity is moving from one neuron to another neuron, and that's how the information is being transferred, and also how functions are being decided about. If there is a decision to raise the hand, so there's one place that I decide to raise my hand, and another place that I raise my hand. So there is a series of synapses between deciding and raising the hands. And these synapses are actually a biochemistry phenomena, and we understand the neurotransmitters behind it. We understand the firing rate, which means the accumulation of all the synapses that are going into one neuron before the neuron is firing back, when the tension of the boundary is too strong. We know that brain controls motoric behavior, reflexes, high brain functions, cognition, language, emotion, and we identify areas responsible for different functions. And a lot of the research that's going on now is to identify the places where things are happening. Of course, we want to understand more than that, but to understand where something is happening is still a lot of research going on, especially in the emotional and the cognitive. So when they raise the right hand, it fires on the left side and vice versa. But in fact, we don't know much. We know nothing about how does the brain work. We don't know how does the network work as a whole. We don't understand how neurons speak to each other. Which neuron, what are the roots? Which neurons, if I drink a glass of wine, a neuron dies, always. So there is another one that takes over. What is the backup system of the neurons? We don't understand especially cognitive and emotional function. We know more about motoric. So we know, for example, to identify the neurons in charge of 3 of the fingers. It's a very slow motion. So 15 years ago, they only knew reaching. Now they also know grasping by 3 fingers, so 2 fingers still. So it's a very slow process. It will take another 100 years before we understand. And language is the highest brain function. And we don't know how to handle huge amount of data. So now it's called big data, this issue, but Neuroscientists are doing big data for years already. They just didn't call it big data. They were just handling data. Not biochemistry neuroscientists, but computational neuroscientists. We localize the problem to a neural network, a set of neurons with action and rules, but we still, this is a picture and some extra Photoshop of the visual cortex. So we look at a smaller piece of the 10 to the 10, but we still do not know how does the brain work. And it's still, in my eyes, the most intriguing question for the 21st century. To study the brain, we need to image from outside what is happening inside. What is brain imaging? First of all, some recording device of the electrical activity, then a forgetful factor. You have to forget what is irrelevant to the question that you asked. Like if we want to understand grasping, and there is also reaching there, so we have to take out the reaching. And a cleaning mechanism, the air condition might affect, the heart beeps might affect, so you have to clean mechanism. And the method that exists now are those that are listed. Intercellular recording is you put a microelectrode into the brain. It's not painful, and it records exactly from a neuron, from specific neurons. One does it on primats because there are not many people that would volunteer, even though it's not so bad. And then the EEG is just electrodes on the brain. That they don't record a certain synapse. They just do some averaging of what happens behind the electrode. So it's an integral and averaging, and then you get something which you want to believe that it's what's going on downstairs, but it's really not because that's what we have, so that's why we want to believe. One of my students did a PhD of changing the EEG recording. But this is it's not something that you earn money from, it's something that you lose money because all the hospitals, they don't want to do it, to change everything, all the machines. And there is the PET scan of brain activity, it's like an X-ray that shows activity. And the very newest machine is the MEG. It detects the magnetic field induced by the electrical activity of the brain. And there are not so many in the world. They are very precise, but they're extremely expensive. I work on 3 machines, and each machine is a little bit different. One I worked in NYU in Israel, and I work now on one machine, the very advanced, the most advanced one in Abu Dhabi. So they record there, whatever I'll explain to you in a moment. They send it to me, and with my student we analyze it and we give it back. So I thought it's a nice science for peace project. We need a smaller one for the head of a child. Why do I put this slide again? Because there is fMRI there in green, in light green, because fMRI is very much used, but it's not a brain imaging, because first you induce on the brain a very high magnetic field, and then you want to see what happens in the brain when it's induced. So it's called sort of invasive. It's not really recording, it's invasive, and then see what happens to it. So that's a different issue. Okay, so now we come to Q. I said in the list that we have to show Q of epilepsy. So epilepsy is a neurological disorder where you have seizures, and the seizure originates in some epileptic focus in the brain. And 30% of the people that have this disorder, the medication that do not help. So when medication do not help, you have to have a surgery. You hope to have a surgery to take out the epileptic focus without causing too much harm to the rest of the brain. Actually, epileptic is a very widespread disorder, about 1% of the people. So it means if you take a double of the class here, or extra 40%, there will be one with epilepsy. But we don't understand that it's epilepsy, because the strong thing is the seizure that we know. But sometimes it's 10 seconds that you lose contact with the environment, and this is considered part of, but you don't treat it. You talk to someone, you think that you are boring because he's gone for a moment, but then he's coming back. So surgery is considered when the patient has only one epileptic focus and it's too much. Quality in life is not good, and also dangerous, because when you fall, you might die from the fall. So how to identify the epileptic focus to take it out? So a prospective patient is subject to EEG test and MRI test, but not only EEG on the scalp. They take out a piece of the scalp and they put the electrode on the brain. It's painless because there are no nerve there that can feel it. But then the results are much better because the scalp is disturbing the recording. If there is agreement between the EEG raw data and the MRI findings, then the way is paved for surgery. But sometimes they disagree. And then you need another kind of algorithm to do it. And we developed an algorithm to determine the epileptic focus and also to eliminate the need for a very invasive operation. This algorithm is used in Tel Aviv, in Michigan, in Chicago, and Los Angeles in order to use it. And in Abu Dhabi, I don't know what to do after they get our results. What are the steps in localizing the epileptic focus? First of all, you have to have the seizure measurement, the EEG during a seizure. Then you do pre-processing. The inverse algorithm is where the mathematics is, and that's including the geometry of the brain model and source model and different mathematical models. And then you have to compare results with pathology. So you obtain the seizure measurement, and you obtain them because there is some automatic tool that identifies the beginning of an epileptic activity. You see in the beginning here, it's very, very close to each other. It almost doesn't look like waves. It almost look attached to each other. And then the pre-processing to take away noise and to calculate the amount of epilepsy to see if it's worth making an operation. And here comes the EEG algorithm. So we have 3 types of algorithm. What you want is you have the outside recording and you want to understand what's coming in, to map the electrical activity inside and find the location of the interesting phenomena like epilepsy. So I'll tell you a little bit, just a few slides about one of our methods, which is the genetic type algorithm. This is based on the mechanics of natural selection and genetics. It consists of selection, crossover, and mutation. So you start with initial data, some guesses to the solution of whatever you want. And then crossover, you take 2 points and you make from it 1 point in some method that you decide. Selection, you take the T best ones, and mutation, you create new points from those that left after the selection process. This is general genetic algorithm. When it comes to epilepsy, you have to adapt it to the brain. You have to decide what is the input, is a possible solution. Each comes with location, orientation, and amplitude. The mutation and crossover are based on the brain geometry, which is very complex, head model and dipole figment, which is source model. I don't say more about that. I just tell you that this is what we are doing, and then there is selection forward equation, and the output comes again. And you repeat it again and again, as you see here. And eventually, as it says here, there is a stability of a process. You keep getting the same points again. So that means the end. This is the result of the algorithm. And of course, it takes into consideration the time frame of epilepsy. This is a little bit more on the adaptation to the brain. One of the easiest ways is to assume that the brain is a ball, but this, of course, is as far as possible from reality. So you know that it has a layered head model, realistic head model, and more than that. And then you test it on simulated data, and you compare results with pathology. And how do you know that you succeeded? Just with the clinical test. If the patient, after the operation that was done with our algorithm, is having less seizures and they are less severe, that's a success. And then, I think I have, because I still have time, because I started later. The next one is sleep disorder. Compared to epilepsy, and since not every one of us has some kind of sleep disorder, otherwise maybe you cannot be a mathematician if you sleep enough. But this is much serious. It's considered one of the reasons for shorter life expectancy. Up to 7 years, that's what the statistics said, if you don't sleep well. according to sleep weight. So sleep disorders are of different kinds. Some of them are, in my family, for example, we all go to sleep late and wake up late, but it comes to extreme. That someone can have 25-hour cycles, so it changes all the time. But the main sleep disorder that the work that I will report is too many arousals. You wake up in the middle of the night and you don't even know it and you fall asleep again. But if there are too many of these, there's not enough oxygen to the brain and you are tired during the day, so you fall asleep during the day. That's no good. It could be come to half of the sleep that you need. So the main goal, and we have two main goals. One, prediction of pre-sleeping behavior. This was funded by Fiat. They wanted to put something in the car that will tell you when you are going to fall asleep, before your eyes are closing and the car is in the tunnel. But when Fiat emerged with Chrysler, I think,
Yes.
Americans didn't want any device in the car that can be sued for that if it doesn't work well. So we stopped, but we continue. And then also prediction of arousals, to see why predictions, because to really know arousals, you have to sleep in the laboratory with the EEG on your head, and it's unpleasant, a very expensive process to put everybody. But if you can see some correlation between arousals and other channels, that is very good. So the experiment, you do simultaneous measure of the following channels. Here are 12 channels, sorry for the Hebrew. Here are 12 channels, but actually there are 16 channels. It's the EEG, it's the EFG, which is muscles, EKG, eye movement, leg movement, pulse, saturation, all these together. GSR is the electricity of the skin, which is very indicative, apparently. So these were the two main goals, but the main tool is to find relationship between the GSR and these other three measures. So EEG recording in sleep research are classified by frequency, amplitude, and the shape. So these are the different frequencies. These are the different shapes. And then together we get sleep stages that are also have to do with the other channels, not only the EEG. The most important is the REM, the rapid eye movement. The whole cycle takes 1.5 hours in most people, but the REM is the last 20 minutes. The last 20 minutes is very important. There is an experiment with a cat. The cat was waken up before he gets into REM, and after 2 weeks the cat died. And how do you know that it's going into REM? Because you see the rapid eye movement. So this is the most important. If you don't have enough of REM, you are in trouble. So we did geometric data mining on different channels in order to see which channels are connected to another channel. This, of course, is a very long work. I'm just telling you that's what it did. And then each confrontation carries a grade, which we call a bit. This allows us to have a probability, and then it's data mining plus probability. We also did it on 4 channels simultaneously. And when we did this per computation distributed confrontation, not on the raw data, but the output of the data mining process, where you see events are confronted with high probability, and then we got the result of the pulse versus saturation, and the pulse versus GSR, and this is still work in progress. I hope I have 3 minutes just to say on the most important thing, how does the brain work. So conjecture on the way the brain works are the following. Chaos, firing rate, plasticity. Chaos, some people say, well, it's random. God did something and it happens. And that's why some people exist and some did not. Firing rate is what I explained before. And plasticity is the way that the brain adjusts when there is a damage. Like I say, drinking a glass of wine, and then there is a new neuron that is doing the work. Synchronization is the method, the theory that contradicts firing rate. That it says it's impossible, that only the accumulation of the firing causes a neuron to fire, and the deltas are not important. So that's what it is. Synchronization means that the delta is important. Compositionality goes with synchronization. It's what is the smallest atom in the brain activity, and fire chain is the final solution, still a conjecture. How does the brain work? If we have some experiment for fire chain, it will be a Nobel Prize. And in the paper, spike synchronization and head motion, our goal was to find unknown relationships that are not related to the firing rate. So it means to disprove the firing rate. And in fact, we did it. We created a new engine in geometric data mining and used probability and stochastic. For algebraic geometry, stochastic was something I had to learn, not only how does the brain, anatomy of the brain. Worked on data from behaving monkeys. You have to work on real data, otherwise you don't really know what happened, because models you can do. And showed that the brain is more sophisticated than firing rate, and synchronization does exist. So we did, the monkey was making drawings. We collected the data of the brain from 8 microelectrodes during the monkey did, and we did this flow chart that we converted the information from the brain data and the hand data. And now I told myself to jump here. There's no time to jump to 130, so I'm jumping to 130. It doesn't go to 130. And we did this experiment of comparing on the real data from the brain and on jitter data. Jitter data that a little bit moved, a little bit. It's not easy to produce 5,000 jitter data, but it's jittered less than the firing rate. So that's why it was a counterexample to the firing rate. And from all these 5,000 jitter data, we put it the distribution of the result, of the score. I told you every day has a score to see how much synchronization there is in that day. And we found where is the score of the original data. And the score of the original data was here. So that was a great success, because if the original data would be in the head of the curve, of course it's nothing. But even if it would be here, it might be a little bit understanding, but certainly not publishable. Maybe here it would be publishable, but here it was a great success and was accepted by the community, which wasn't easy because they worked on firing rate for their entire life. So this was accepted by community that synchronization exists. So none of the 5,000 jitter data reached the original score. So we had this window of surprise versus jittering window, and we found the significance of 0.2%, and it spikes whole information in a time resolution of 3 milliseconds. That's what we found out. And we had, unfortunately, to do it with the second monkey also, because I didn't know, I'm not a biologist, I didn't know that when you send a paper to a biology paper, you have to do it on 2 monkeys. Because if you prove that there is an elephant that speaks English, so there is an elephant that speaks English, why do you have to prove the statement there is an elephant that speaks English? But that wasn't good. To say there is only 1 monkey, we had to do 1 monkey, and the guy got his PhD 1 year later, but we proved what we wanted. It was even less than 3 milliseconds. And the end, I put a question mark, because it's not really the end. We still have to work a lot in order to understand how does the brain work. Thank you.
Questions?
How does the brain work?
Yep.
Why do you need to do the experiment on the monkey?
Sorry?
Why do you need to do the experiments on monkeys?
Because people don't volunteer to do it.
Oh, because they have to open the skull?
You have to not open. You put microelectrodes into the brain of the monkey when he does the drawing.
Oh.
And if you, because whenever you do a model, it's just not real data, you can do whatever you want. So in order to understand, you have to go to a real data. It's not fun. It's not fun, but the monkeys are very well treated. They work 4 hours a day only. They have a living room, they have a study, they have a bedroom. The students from the art department did drawings all over the walls. They have windows. And that's their job. The job is to sit 4 hours and make drawings and drink juice when the drawing is very nice. My monkey, I didn't show you the picture, he liked cusps. So that's a nice twist, that my monkey would like cusps.
Other questions?
Yeah.
If not, let's thank Mina
Yes,
again.
yes, please, what is it?
Are you going to do a more specialized scope? There was a lot of statistical analysis going into it. Some things look like time series. Maybe
Well, next time when I'm in
analysis.
Miami, next time in
Next time
Miami.
you're in Miami, not now, not this time.
No, this time, the conference is very, very strict. Yes,
One of the things that I've always puzzled when people do recordings from the monkey cortices, there is so much there's so many recurrent circuits across the cortex. So so how do you approximate that in a model where you don't know how many additional inputs there are?
because these microelectrodes, they touch the neuron. The microelectrode is only recording from 8 neurons around it. And since we know where the motor cortex is, I told you we know reaching, we don't know grasping, so we put it exactly into the motor cortex, and we have a list of the neurons. This is a very enlightening that with 32 neurons we could make this proof that there is a synchronization. But what you are asking about the overall activity of the brain, that's a general question. When you do from outside, the EEG, you don't know what the EEG is recording also, not only that. So part of the challenge is to do this pre-processing, to take out whatever is not relevant, or spike sorting. It's not easy, but a lot of it is conjecture, but some of it is real data that you already know where is it coming from. But it's a extremely important question. It's the main challenge in neuroscience.
Other questions? Or if not, let's thank Mina again.